Okay, welcome back everyone. In this video, we're going to take a look at another concept, gravitational potential energy, which is different now that we're looking at gravity in a more encompassing way. What I mean by that is that we used to write potential energy is equal to mgh, and that was the potential energy due to gravity. But what we know is that g itself is not always 9.8. G, in other words, the strength of the gravitational field, or the acceleration due to gravity, it depends on your position. So when people used to go up in the space shuttle, they would orbit at a height of 320 kilometers. And at that height, if you calculate little g from gm over radius of Earth plus height squared, we talked about that equation last video, you actually get something like 8.85. So there's two weird things that come out of this. Number one is that, contrary to what you thought, astronauts are accelerating. They're falling. They're falling. It's not 9.8, it's more like 8.9 or whatever, but they're constantly falling towards the Earth. It's like always being on that first drop of Raging Bull, continually. Now the second thing is that we can't use this equation if g keeps changing. So what I'm going to do is give you an equation for potential energy, and in the next video, which is optional, I'll actually derive this expression. In order to fully derive it, I would need to use calculus, but for now I'm just going to tell you about it. Okay? Now one thing that's very important is that in the book, potential energy is also written with a U. So it's important to see and be familiar with both of these notations, okay? And so this is, in this case, gravitational, but in general, U stands for potential energy. Remember again that potential energy is energy due to an object's position. So that's why it's so important to think about the new acceleration of gravity, g. Okay, so here's the equation for gravitational potential energy. So, potential energy due to gravity is equal to the gravitational constant times the product of both masses over the radius. Not the radius squared, just the radius. And there's a negative sign. Now these are all things that I'll explain in more detail in the next optional video. But this is how you calculate the potential energy stored due to position between two objects. I mean, we just kind of take it for granted that, oh, here's a 1 kilogram book and it's sitting, you know, 2 meters above the floor, so it has potential energy of mgh. Use 10 for gravity. Oh, that's 20 joules. We just take that for granted, but what we don't often think about is that this potential energy exists because the two objects, the Earth and the book, are being drawn toward each other. The potential energy can be converted into kinetic through the force of gravity. So anyways, this is the equation for potential energy. And there's a couple things that I want to point out about this. One is that it involves both masses. Okay? So it involves two masses. Another one is it's a 1 over r, not a 1 over r squared. That's important. Alright, and that's kind of a calculus link. You'll learn about that later, but it's kind of cool. And the next important thing is it's always negative. And as a matter of fact, we have to be careful, because what if r was equal to 0? What would happen to that equation? Well, it would explode. Okay? So what we do is we say that the potential energy, or rather, the potential energy due to gravity, here's another piece of information, is set to be equal to 0 when r is equal to infinity. And this is a really, really weird concept. The book has a nice graph that shows this. And this is, I guess I'll have to scoot down a bit more. Here's potential energy, and here's radius. And it goes kind of like this. So that the potential energy gets less and less negative, but it never reaches 0. Okay? Now here's kind of an analogy. Let's go back to on the surface of the Earth. So here's the surface of the Earth, and let's say that we state that this is where h is equal to 0. So this is where normally potential energy is equal to 0. Okay? Well, now let's actually cut a hole and put a guy at the bottom of a deep well or something like that. So now his height's going to be negative. And so the further down you go, the more negative his height's going to be, and the more negative his potential energy is going to be. So what we're saying is that with this expression, the negative gmm over r, we're saying that you can never get to the point where it's actually equal to 0. That would be when r is infinite. You can get pretty close. And you can also never get quite to the point where you have infinite energy, because you can't get two objects to be separated by 0 distance. So r can't be 0. So those are two ways that this equation actually works a little bit. Now if you're kind of hung up on this whole setting it equal to 0 at infinity, well, remember back in chapter 5 there was a question about your house, and it was talking about the changes in potential energy as you went from your basement at a height of 0 to the first floor at a height of 25 meters. I'm making these numbers up, or 25 meters. Okay? Now in terms of a change in potential energy from one floor to another, does it really matter what I label these as long as the change is the same? Like, what if I labeled the bottom level not as 0 but 22? Well, it's still 15 meters to get to the next level, and it's still 10 more to get to the next one. Okay, well, what if I labeled it negative 3.14 just because I feel like it? Okay, well, now this one's going to be 12.14. You get the idea. So the labels for the heights aren't that important. What's important is the differences in the position, and that's what it's all about. Now that difference in position is what allows us to use this equation for gravitational potential energy. And if you're still not feeling too settled about this, I'll give a little bit more rigorous proof, well, not quite a proof, in the next video, which is optional.